Alrighty, folks, thanks for joining me. I hope you've had a good week. I ask people all the time what's been new, and no one has anything to say that's different this week than last week. So I hope it's better for you than it has been for folks in my world. But here we are talking about trigonometry for the SAT and ACT. So I'm going to start at the very basics, kind of fundamental building blocks of SOH CAH TOA, and then try to run through everything that I've seen that's popped up on the SAT, ACT, going from easy to kind of gnarly at the end. As always, if you have questions, throw them in the Q&A, questions, feedback, and we'll roll into this. Okay, so the most fundamental thing to know about trigonometry is it's ultimately based on applications of the Pythagorean theorem in all kinds of wackadoodle ways. Real math teachers despise the term SOH CAH TOA, but I'm not a real math teacher, so there we go. So if we start with an angle of x in a right triangle, we could agree that this side is the hypotenuse. And then relative to angle x, this side is opposite x. This is silly, but kind of this is where a trumpet or a cannon, it kind of shoots out, and that side is the opposite. Now, we're missing one more side. This side is the adjacent. Now, sometimes people ask me, how do you know this is the adjacent? Why isn't that one the adjacent? They're both beside angle x, which is true. However, because this is the hypotenuse, it can't also be the adjacent, okay? So as we apply this, sine is the ratio of the opposite side over the hypotenuse, okay? Cosine, the cosine of this angle x is the adjacent side over the hypotenuse, and the tangent, OA, is the opposite side over the adjacent side. So for many of you, this is kind of old hat, but let me just run through one problem really quickly to kind of put this into context. Then we'll move on to word problems. So let's pretend we have a right triangle. I'm going to call that x. I'm going to call that theta. Now, if you've not seen theta, you're like, what is that? Is that an O? Is it a circle? It's actually a Greek letter. A lot of very frequently used in trigonometry because it's not confused with anything else because it's a Greek symbol. So let's pretend that this side is 3, this side is 4. Make that a right triangle. That side is 5, a typical Pythagorean identity, which a lot of you, of course, had done in geometry. So just to get people up to speed again, particularly if this is new, I'm going to ask for the sine of x, and you can do this at home if you want to follow along, the cosine of theta, the tangent of theta, then sliding over here to fill it out, the sine of theta, the cosine of x, and the tangent of x. Okay. If x is our angle, and again, for basic trig, I always write out SOH CAH TOA, just because it helps me avoid making little mistakes. So the sine of x is the opposite over the hypotenuse. So if that's my angle, the opposite side would be 3, and the hypotenuse is, of course, 5. Cosine of theta, cosine here, this will not be the adjacent side. This will be the adjacent side. When I have this angle, here's the side that's beside it. So 3, and again, a hypotenuse of 5. And then tangent of theta, again, not this angle, but up there, my theta, will be the opposite of 4 over the adjacent of 3. Sliding to the next column, the sine of this angle, what side is opposite that angle? Well, again, the trumpet, the cannon, whatever, straight across from it will be 4, hypotenuse of 5. Back switching over here to keep you guys jumping, cosine of x, the adjacent side will be 4 side by side, and hypotenuse of 5. And then lastly, tangent of x, an opposite of 3, and an adjacent of 4. Okay, good enough, pretty straightforward. You're not probably going to see problems that are like that. They're going to put it into word problems because they hate us. So what do? They say if a ladder of 20 feet length leans against a wall at base angle or angle relative to the ground, they may use more words, I'm going to use fewer, of 60 degrees, how far from the wall does the ladder extend? And again, lots and lots of words they'll do this in. So sometimes they'll give us a picture. A lot of times we have to draw the picture. Any geometry problem without a picture, any trigonometry problem without a picture, make one. it makes things that seem kind of abstract a lot more concrete, and obviously concrete is happier than abstract. So let's draw a ladder. Not a talented artist, you guys already knew that, but let's pretend our ladder is 20 feet in length, okay? And it's at an angle of 60 degrees. How far is this length? What's this length of the ladder from the wall? Again, assume a 90-degree wall going straight up and down. So again, I'm always going to write out SOH CAH TOA. So I ask myself, I have this angle of 60 degrees. Awesome. What do I know? What am I trying to find? Well, I know that this is 20. I should have done 20 feet, not degrees. I know that that's 20, and that's the hypotenuse. And I'm trying to find this side x. Well, relative to x, is it the opposite or the adjacent? It is, of course, the adjacent. So therefore, I'm going to use cosine and say cosine of 60 degrees equals x over 20. What's the next step that I do? Sometimes in the problem, they'll actually tell us what cosine of 60 degrees is. It's 0.5. But if they don't, we have to do that on our calculator. So you grab your TI 83, 84, whatever, and put that on, and I will do cosine of 60 degrees. And happily, that's 0.5. Now, it's also possible, just to run you guys through this, you try this again, and you do cosine of 60 degrees and get a much uglier number, like negative 0.9. What the heck is that all about? So with angles, there are two types of ways that angles can be measured, either as degrees or as radians. We're going to talk about radians in a moment, kind of what those actually mean and why do we care. But for now, I want to point out that on your calculator, the mode button right next to the second button, we want to press mode, and we want to check what mode we're in. So you see down here, we can have radians or degrees or radians. Which one should it be? Well, if the angle is expressed in terms of degrees, we of course want to use degrees. So we hit enter there. If it was expressed in terms of radians, which basically means an angle in terms of pi, but we'll talk about that in a moment, then we'd use radians. So I'll hit enter there, and then I'll quit, and I'll go back and say cosine of 60 degrees. Oh, thank goodness, a much prettier number. So cosine of 60 degrees we just determined is 0.5. So 0.5 equals x over 20. I kind of like to undo these by cross multiplying, because sometimes they'll give you goofy things like the tangent of 30 equals 15 over x, and it's getting a little more complicated there. So I like to put a 1 there and then just cross multiply. 1 times x is x. 0.5 times 20 is, of course, 10, and so that means that x equals 10. But again, you'll sometimes get these things being gnarly. I try to undo them with the Pythagorean theorem. Otherwise, people divide this by 15, which is fine, but then that should be tangent 30 over 15 doesn't equal x, it's 1 over x, and so that's why we cross multiply. We avoid making that mistake. So most of the trig that you're going to see is really going to be nothing more than SOH CAH TOA, like we just did there, and you can write that down. And then word problems, and all kinds of word problems of airplanes and ladders and trees and shadows and all that stuff. And it's all fundamentally about doing Pythagorean theorem SOH CAH TOA, okay? So let me move on to stuff that gets more complicated, because as I promised, there's a lot in here. Where did I put my list? I know I have a list. There's my list. All right, so next thing we're going to talk about inverse functions, which doesn't show up very frequently, but I might as well cover our bases. So you could have something, if this is 3 and 4 and 5, you might want to know what's that angle. Well, the way that we could do that angle, let's say we're going to use tangent. I could write the tangent of x equals 3 over 4, excuse me, I wrote 3 over 4. But the question is, what angle gets me 3 over 4 or 0.75 or anything in that ratio, 30 over 40, blah, blah, blah. To figure out what angle x is, to get rid of this tangent and to get just the angle x, what we do is what's called the inverse tangent. So it's kind of like you undo a square root by squaring both sides, right? Or you undo a square by taking the square root of both sides. It's a different math operation. So I'll do the inverse tangent of the left, and I'll squeeze this in here, the inverse tangent of that. On the left side, the inverse tangent of tangent, they kind of nullify each other, and I'm left with just x equals the inverse tangent of 3/4. So then go back over to your calculator to find the inverse. You see tangent here, the inverse tangent, tan to the -1. We do second inverse tan, again, type in 3 divided by 4, and that will get us 36.8, roughly 37 degrees, and that will be our angle. So you can get a problem like, if cosine of theta equals 0.5, and we know that that's 60 degrees because we did that a moment ago, find sine of 2 times theta. Again, if I do that on my calculator, second cosine 0.5, I'll get 60 degrees. So then I could do the sine of 120 degrees, put that on a calculator, and it'll tell us what it is. It'll be √3/2 or 0.877, blah, blah, blah. So not a really complicated thing. SAT sometimes uses, in place of the inverse sine or the inverse cosine, what's called arc sine. It's the same thing, it's just a different way of describing it, or arc cosine. This probably shows up even more on the subject test if you take that, and it's just language. So here's a complicated version of this. Find sine arc tan 5/12. People are like, what on earth does that mean? This is more complicated. So if you're a little freaked out by this, and I know I'm going fast, don't panic. This again is all recorded. You can go back and watch it again. I'm going to start from the inside out. Arc tan means the tangent of what angle gets me 5/12. So the tangent of what angle gets me 5/12. So you know what I'm going to do? I'm going to say that angle. The tangent of that angle, x, gets me 5/12. Well, I could do two things. I could do this on my calculator and calculate the value, but I'm not going to do that for now. Calculate that and then do the sine of that angle. And I'll tell you what it's going to get me. It's going to get me 12/13, or that decimal. For those of you who are playing along at home, race ahead, double check that I'm right. Oh my gosh, I did that wrong. It's going to get me 5/13. So race ahead, you can check that on your calculator. Do second tangent of 5/12. Actually, let's do this. Why not? Second tangent of 5 divided by 12 gets me that funky angle. I can then do the sine of that angle. Second answer will give me that, if the calculator is kind, and will actually turn that into a fraction for me. We get 5/13. How did I know that? Well, when I made the problem, but also arctan of 5/12 says the tangent of what angle gets me 5/12. So I just made a little right triangle. Like we said, always make a picture. And so it's the tangent of that angle that's 5/12. I could have drawn it here. I could have said, I want that angle to be 5/12. Well, now that we have a right triangle, we can just do Pythagorean theorem. 5 squared plus 12 squared equals, call it h for hypotenuse, right? 25, you guys know this, but I'm going to do it anyway. 25 and 144 is 169. Be sure you square root it. Be sure you square root it. 13 is h, so that's 13. So then the sine, and remember that whole thing's just the angle of which the tangent of that gets me 5/12, becomes the sine of that angle x. The sine of that angle x is, of course, the opposite, 5, and the hypotenuse, 13. Okay. That's kind of considered a pretty sophisticated problem, kind of harder level stuff, ACT, harder level ACT, harder level subject test. More basically, you might just have to do this. Second cosine on your calculator, get the angle, stick the whole thing back in. Okay, that's fun. I keep losing my list. I will try to do a better job. All right, some other functions, some other identities you need to know. We just did, so CAH TOA and word problems with that. Said sine is opposite over hypotenuse. Good grief, sorry, cosine adjacent over hypotenuse. Tangent opposite over adjacent. In addition to those, there are some other trig identities. They get tested occasionally. There is cosecant, secant, and cotangent. It's written out as cosecant, not that you'll see that. Secant, not that you'll see that too much, and cotangent, not that you'll see that. So you're wondering, what the heck is this? Cosecant is simply the reciprocal of sine. It's 1 over sine. Secant is the reciprocal, or 1 over cosine, and cotangent is the reciprocal of tangent. You might have thought that cosecant would be 1 over cosine, because those kind of look like they go together, and secant and sine, but they don't. I'm not going to get into it. You simply need to know these. So you'll get identities where they'll say, you know, the tangent of something times the cosecant of something equals what? Well, tangent, oh, we'll talk about this in a moment too, but trust me for now, tangent is sine over cosine, and secant is 1 over sine. So if I multiply those, I get 1 over cosine, which is the same thing as secant. Or we could have done the tangent times cosecant. Tangent is opposite over hypotenuse. Cosecant 1 over sine. What do we say sine was? Opposite over hypotenuse. Dividing by a fraction, Did I do that right? Just double checking. Yes, I did. Dividing by a fraction, we multiply by the reciprocal, so we get h over o, right? Multiply. Then this would get us o times h over a times o. Cancel out, we have h hypotenuse over adjacent, which is the reciprocal of cosecant, which is adjacent over hypotenuse. That was a lot of math. For those of you who haven't done that yet, I apologize, I went pretty fast on that. You can do those a lot slower. All that you need to know is that cosecant is the reciprocal of sine. So instead of opposite over hypotenuse, it's the hypotenuse over the opposite. And the same thing all the way through for sine, for secant and cotangent. These do not show up very often, but you might just want to file them away. And again, this whole thing is recorded. You can go back and watch that. You can also slide over good folks at the Khan Academy who can give you like 1,000 practice problems on this for practice. I'm just trying to give you an overview of everything I think you may see involving trig for the ACT or the SAT. Okay, Pythagorean theorem. Hold on, I had a quick note for myself. Oh, yes. I guess I'll do that one there. Nah, I'll come back and do that later. Okay, Pythagorean identities. Well, beyond these guys and all the stuff we just did, there are kind of two other identities that get used a lot on the test. One is that tangent can be sine over cosine, and I'll tell you why in a moment. And the Pythagorean identity, the cosine squared of an angle plus sine squared of an angle equals 1. And let me just take a moment to explain both of those. So tangent, we know, is opposite. Let's write it out again. We always benefit from that. Tangent is opposite over hypotenuse. Okay. Sine, opposite over adjacent. I said that wrong. Sine is opposite over hypotenuse, and cotangent is adjacent over hypotenuse. So again, if we take this, we know that when we divide by a fraction, we multiply by its reciprocal. So these cancel out. I just do 1 on the denominator, and I get O over H times H over A. Those guys cancel out. And I'm just left with O over A, which again is what tangent equals. So it's simply an identity, but we'll save you some time. We'll do a problem with this in a moment. Slide up, sorry about that. Cosecant squared plus sine squared of x equals 1. Why? Well, like I said at the very beginning, pretty much everything in trig is some kind of a wackadoodle application of the Pythagorean theorem. So let's call this, again, opposite, adjacent, and hypotenuse. We could agree that, let's do this 2 ways. We could agree that the opposite, I'm going to do this, the adjacent squared plus the opposite squared would equal the hypotenuse squared, right? A squared plus B squared equals C squared. Now, if I wanted to go a little nuts and divide everything by H squared, I would have A squared over H squared plus O squared over H squared, and that would equal, well, that would equal 1, right? And then this could be A over H squared, because A squared, H squared, and this would be that. And what did we say A over H is? Why? We said it's cosine. Oops, let me slide up again, sorry. We said it's cosine of that angle squared. And O over H, we've done before, is sine And so we've just proved again that cosine squared plus sine squared equals 1. It's just the Pythagorean theorem. Or find it one other direction. If you took, this way. If you took cosine squared plus sine squared and said that equals 1, that would be O over, H over A over H squared plus O over H squared. If I multiply everything through, just go in the opposite direction, and then multiply everything by H squared, we're back to the Pythagorean theorem. So let me show you two quick problems with this. So again, the things we'll use, once tangent of theta equals sine of theta over cosine of theta, and cos squared plus sine squared, I should work that in, plus sine squared, pardon me, equals 1. So what would this look like? If tangent of theta equals k, find cos theta in terms of k. Now, we know from doing our plug-in and number stuff, we can kind of ignore that because it makes us a little bit nuts. I'm just going to get rid of it. I'll give you some answer choices here. You guys can play along. See which it is. You might already be done, but I'm going to write out the answer choices anyway. So how do we do this? Well, we know that tangent of theta is also sine over cosine. So if tangent of theta equals k, then sine over cosine equals k. So I'm going to rewrite that cleanly. Like I said before, I kind of like to undo ratios by just dropping a 1 and cross multiplying. So that means sine times 1 is sine equals k cos theta. So if I wanted cosine, we didn't need this, we can get rid of that. If I wanted cosine, I would simply divide both sides by k, and cosine would equal sine over k. And there's my answer. Okay? So that's one problem. Second problem might be something like this. I'll give you two. If cos squared theta minus q equals 3 minus sine squared theta, what the heck does q equal? All that we need to do, knowing that cos squared plus sine squared equals 1, is put those things together. So I'm going to add sine squared to both sides. I know you guys might take a shortcut. I'm a fan of kind of writing out work because I hate making silly little errors. So that means this whole thing is 1, so 1 minus q equals 3. I can add q to both sides if I wish to. 1 equals 3 plus q, subtract 3, and I know you guys know before I run out of space that that's negative 2 equals q. Okay? Problem was on either an SAT or ACT, I can't remember, was something like cosine squared of 9m plus sine squared of 9m. Does that equal 1? Does that equal 9? Does that equal 9m? Does that equal what the heck? I have no idea. And the short answer is it will equal 1 because this is the angle, and the angle can be bloody well anything. If you don't trust me, do like we did last week, plug in a number. 2 weeks ago, because last week was reading comp. Say m is 2. Do on your calculator cosine of 18, find that value, and square it. By the way, cosine squared of 18 is literally doing cosine of 18 and then squaring the value, not squaring 18 and doing the cosine of that. So you can put this on your calculator, do cosine of 18 squared, you'll get some wackadoodle number. Do sine of 18, square that, and then find some number, and it'll probably be like 0.99. You get a little bit of rounding error, but trust me, it'll equal 1. Okay, how we doing? You guys brain hurt yet? Mine does. Let's roll on. That was Pythagorean identity. Oh, by the way, if you're doing these in school, these can be so irritating to do all this identity to prove them. You only have to memorize this one. If you memorize that one, you can create all the other ones because you can do things like divide everything by cosine squared. Just like a common denominator, you're not changing the value, just what it looks like. That, of course, becomes 1. Sine over cosine was tangent. So what do you think sine squared over cosine squared would be? You're right, tangent squared. And then if you remember from our previous page, that 1 over cosine is cosecant or secant? Secant, right? It goes backwards. You'd think it would go the other way. Will be secant squared, and that's one of our identities. We could have divided by sine squared and get the other identities. So as long as you know one, you can create all the other ones. Okay, so what's a radian anyway? I always get that. What is a radian anyway? Like, why do we need, well, I could kind of be a pain in the neck and push back and say, well, what's a degree? We agree that a degree is a thing. That sounds kind of weird. A radian is another way of measuring angles. And this exists in real mathematics for real mathematicians, of course, of which I'm not one, but it matters enormously because the idea here is really that if you take a circle, and you guys remember that pi is an irrational number, quick sidebar, extra credit, a rational number comes from the ratio, you can see that ratio, rational, of two whole numbers. So 3 over 4 is rational, 117 over 9 is rational, negative 3 over 2 is rational. Anything that comes out either that ends as a whole number, as a decimal, or even a repeating decimal will be rational. But numbers like pi or the square root of 2 are irrational. They're decimals that go on forever. There's no repetition. They never stop. So pi is a really funky number. Maybe you guys did Pi Day and tried to remember the numbers. Oof, there's a lot. Good luck. So the problem is, if you take a circle and try to cut it up into very neat little measurements of exactly 360 degrees, there's a slight imprecision there. Doesn't bother me, my life carries on, my watch, good enough. But if you're a real mathematician, or if you're putting me on a spaceship and sending me to Mars, you know, gazillions of miles away, those little tiny differences over long distance become a real problem. So again, in physics, in engineering, they use radians, they don't use degrees. Okay, so how does this work? The fundamental thing that I want you to know is that 360 degrees equals 2 pi radians. Ideally, that's not too hard to remember because maybe 2 pi r, like circumference, you know, remember that from a circle. Or that 180 degrees is pi radians or pi rads if you're being, you know, lazy as I am. And from that, you can figure out everything else. So 90 degrees would, of course, you can figure that out, be half of that. And 45 degrees would be half of that. But you can also get questions like find 225 degrees in radians. Or find 5 pi over 6 in degrees. How do I do that? Now, some of them may be really down with this. You may know to multiply by this reciprocal. Because I keep talking about, some people love this. I'm not going to do that. I'm going to cross it out as soon as I write it. Because we've talked about doing a lot of problems with ratios. And it's a really helpful way to avoid making little mistakes. So I'm going to use this one. 180 degrees is pi radians, which means that I can set up a ratio and solve anything with that. Now, if I have degrees on top and radians, excuse me, on the bottom, then of course I need to do degrees on top there and x radians there. Again, like I keep saying, I love to undo these by cross multiplying. It makes it awfully hard to make a mistake. So 180 times x is 225 times pi rads. Pretend that says radians. If I want just x, I won't divide by this, I'll divide by that, cancels out, I have x equals 225 over 180. The test makers will probably write that as 5 pi over 4 radians. You could, of course, do that on your calculator. If you don't like fractions, just throw that on your calculator, get 1.25. You could use that little button we showed before of the arrow frac. You guys remember this, a good thing to review in case you don't know this one yet. Doesn't quite make this thing worth $120, but still, 225 divided by 1.25, go back over the math button. First one is arrow frac, hit enter twice, and I proved myself correct, thank goodness, 5 pi over 4, okay? Now, another quick thought about radians. There's a question of why do we even need to know this? Well, it really comes from the unit circle. So let me just walk you through this. You could have a 3, 4, 5 triangle, We did this before, found out that was 36.8 degrees. I'll call it 37. You could have a 3, 4, 5 triangle in the first quadrant, right? You could have that in the second quadrant. What, if anything, would change if you were in the second quadrant? The thing that you want to keep in mind, again, almost everything we do at Trig is based on Pythagorean theorem. But once we move out of the first quadrant, we have to pay attention to what becomes negative. And we know that over here, the y values are all still positive, but the x values are not. So we get that. We can have this triangle over here. 3, I'm used to writing upside down, 3, 4, 5, negative. The hypotenuse always stays 5. So this gets complicated depending on your math class, but the idea is we can do all these triangles that you're used to doing, 30, 60, 90 triangles, but we move out of the first quadrant into the second quadrant. So 1/2 root 3 over 2 if you've done that, 1 or 1 root 3 and 2. But in the third quadrant, and I'll do the second quadrant, if that's 30 and 60, that would be 1, that would be negative root 3, and that would be 2. Okay, pause for just a second. So in a unit circle, when we have these triangles move out of the first quadrant, we really have to pay attention to the angles. And it's the idea that you take an angle and it gets a little bit bigger and a little bit bigger from 30 degrees to 45 to 60, all the way up to 90. As it goes past there, we get 90, maybe this becomes 110, smaller, 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 smaller. 0 degrees, 90 degrees, 180 degrees, 270 degrees, back around to 360. Curiously, if you want to make that angle and go more than 360, you're totally allowed to do that. If that was a 60 degree, what they call a terminal angle there, where it ends, 360 plus 360 would make that an angle of 450 degrees. So a problem that the ACT especially loves is which of the following angles are not the same. Oh my gosh, Ned, you can do that? I should have done this. Squeeze it in there. 320, 760, something like that. So if I had an angle of 40 degrees and I made a full revolution, came all the way around again, 40 plus 360 would be 400. I could add 360 again and go to 760. Or, bear with me, if I'm at 40 and I go instead of this way, if I go that way, which means a negative direction, I subtract 360 to come back from where I was. And so negative 320 actually equals, coterminal means it ends at the exact same place as 40 and 400, blah, blah, blah. An uncommon problem, but it does hop up once in a while. Again, the key thing to know, 40 degrees, go 360, go 360, go 360, or negative 360, go the other direction, you'll keep ending up in the same place. Back to radians. So, 0 degrees, 90 degrees, 180 degrees, do we still care? Maybe, 270 degrees, 360. Or radians. What did we say a full revolution was? We said a full revolution was 2 pi radians, which means that half of that, the one that we used for our ratio, was pi radians. So what happens is this is half of 180, so this is half of a pi radians. And then this would be pi radians. And then this would be pi and a half radians, 1.5. And then this would be 2 pi. Okay? So what might this problem look like? Here's a funky problem. I'm going to try to trick you guys a little bit. I'll let you actually play with this for a minute. But here's the deal. If, let's see here. If tan of theta equals 6 over 10, and theta is greater than or equal to pi over 2 and less than or equal to 3 pi over 2, find sine of theta. So I can give you your answer choices. Let you guys work on that for a moment, and then I'll walk us through that. Actually, I'm going to change that, make it 6 out of 8. We'll get happier numbers that way. You guys who have already started the Pythagorean theorem, I apologize, but this will make your numbers just easier. Let's do 8 over 6. We'll do negative. 8 over 6. We'll do negative 6 over 10. We'll do 6 over 10, and we'll do change that. Okay, so here's the deal. Pi over 2 is here. 3 pi over 2 is here. So we could have a triangle that's here, or we could have it be there. And it matters where it is, because when we're in the outside of the first quadrant, we have stuff that's negative. So let's go through and play with this. If sine of theta, I should have put the theta there, I sometimes get lazy. If tangent of theta is 6 over 8, I'll redraw it here, we would have 6 and 8. Okay? You could do Pythagorean theorem and make that 10. You probably already know that. Or we could do it over here, 6 and 8 and 10. Now the question is it the second quadrant or is it the third quadrant? I don't know. It depends on the negatives. Because if it's here, if it's 6 and 8 here, this 8 is negative. The x value is negative, but the y value, the sine, y value is positive. So tangent would get us positive 6 over negative 8. Whoops, that's not what we want. We want it to be in the third quadrant where we have negative 6 and negative 8. The hypotenuse, again, by definition is always 10. So that means that for this angle, the sine of this angle will be negative 6 over 10, rather than 6 over 10, which is really an easy one to put. Okay? So that's putting together all of our SOH CAH TOA stuff and unit circle and radians, kind of a complicated problem. Okay, 2 more things we get to talk through. I guess we did that. Unit circle periodic functions. Yeah, let's talk about that. And then trig for non-right triangles. So if I go back to here, what we talked about, we have an angle, right? Say that was 30 degrees. We can go all the way around, comes back to 390. We get the same place. If I made a graph of sine of x, or sine of theta, excuse me, when my angle is really small, because sine is the opposite over the hypotenuse, I have a really small sine value. As my angle gets bigger, this thing pops up, my sine value, the y value, the opposite, gets bigger, right? As this gets bigger, that gets bigger and bigger and bigger and bigger and bigger, all the way up until I have a triangle that's basically straight up and down, in which case my opposite and my hypotenuse are the same darn thing, okay? So this means, and then if I keep going, and then we'll graph this. If I keep going, my angle gets bigger and bigger and bigger. It goes past 90, goes to 110, whatever. Remind me to talk about this for a second. That'll help you in a moment, guys. It gets smaller and smaller and smaller until it comes all the way back down to just about 0. Then it gets bigger again, but this time in a negative direction, okay? Now, if I graphed all these things, if I started at 0 degrees and I graphed, saying y of sine of x or sine of theta, what's the y value? I mean, and how high is it? 0, 0.1, 0.2. I would get bigger and bigger and bigger up until I hit a value of 1, which would be right there, right? And when does that occur? Well, that's when 90 degrees. We're going to do this first with degrees because most people are a little more comfortable with that. Then we'll go back and do this with radians. So 0 degrees, 20, 30, 40, 50, 60, all the way up to 90 degrees. Then it started coming back down, right? All the way back down here to 0. And so that's where we see, we kind of get this half a circle up here. As we came down here, the y values became smaller. It's the exact same measurement, the exact same shape. It's just that everything is negative. And then this is what's called a periodic function, means it goes on and on and on and on. It does the same thing over and over and over and over. So like the period of a moon, 28 days from full moon to no moon back to full moon, on and on and on. So let me tell you the basic idea of a sine function, then we'll do some other ones and we'll talk about the radians, like I said. So the basic sine function goes up to 1, down to -1, okay? Because that's what we saw. We want y value went up to 1, then came all the way back down, smaller and smaller and smaller, down to -1, and then back up. How long to make a full revolution? Well, all the way around, 360 degrees. So this thing, how high or how low, is what's called the amplitude, how high or how low it is, the amplitude. The period is how long it takes for, you know, one revolution, basically. One revolution. 360 degrees. There's a really nerdy formula. Again, this is pretty sophisticated, but they can ask you about this, of y equals a sine bx plus c plus d. A, again, the amplitude. The period, this is kind of complicated, the period is 2 pi over b. So let me show you. If I said y equals sine of x, we said it would have gone up to here and back to there, would have gone up to 1, down to -1, and would have taken 360 degrees. If I said y equals sine 2 sine x, all of my y values would have been twice as great. So now I'd have the exact same shape, it would just be taller. It would go up to 2 and down to -2. Okay? It would still make a revolution of 360 degrees, but we said that 360 degrees was also 2 pi radians. So the proper, when you see these things on the test and in your math classes, they'll do this in terms of pi. So 2 pi to go there, pi to go there, half a pi is where our 90 degrees was. So that's y equals sine x, again, an amplitude up to 1, down to -1, so amplitude of 1, and our period was 2 pi. Here's the slightly complicated thing. If I said y equals sine of 2x, then whatever, or 2 theta, whatever value I stick in for theta, I double. So before I'd stuck in pi over 4, I'm going to get twice the value of that. It's going to be the same thing as though I had done sine of pi over 4, or sine over 30 degrees becomes the same thing as sine of 60 degrees, which means that I don't need 2 pi to make a revolution. I can do it in half the speed because everything, or half the space, because everything is doubled. So y equals a sine bx plus c plus d. This is the amplitude, how high or how low. The period, how long it takes to repeat, is 2 pi, a regular period, divided by a number. If there's just a 1 there, then the period is 2 pi. If there's a 4 there, then the period is 2 pi over 4, or simplifies to half a pi. Okay? These things don't show up too much, but this basically creates a side-to-side shift, and this makes a vertical shift, just like if you had y equals x squared versus y equals x squared plus 2, this will have, sorry, y equals x squared. Let me give a new page. Oh, I have a lot to say. It's trying to, a lot to get into a short period of time. Y equals x squared quadratic. Aha! Y equals x squared plus 2, a quadratic that has been shifted up to, because the y-intercept, the value in x equals 0, we get a y value of 2. So if you had y equals sine x, like that, if you did y equals sine x minus 3, 1, 2, 3, everything shifts down by 3 and does the exact same period, but just lower. So here's a slightly fun one. This was on either SAT or Forget. Find the range, or something like this. Find the range of y equals 2 sine 3x plus 4. Okay? So we know that the number in front is the amplitude. So if it was just that, it would go up to 2 and down to -2. But it doesn't. This, we don't have to worry about that. It affects the period, not our problem. But that shifts the whole thing up by 4. So instead of going from 2 to -2, we add 4 to everything, and it goes to 6 and 2. So our range is now 6 and 2, or instead of starting there, we could have gone 1, 2, 3, 4, and then gone up 2 from there, and down to, did I do 1, 2, 3, 4? That's hilarious. Down to 2. It goes on and on and on and on. starting at 4, range of 6, and down to 2. Last two things. Trigonometry for non-right triangles. I thought you said everything was Pythagorean theorem. Well, yes, but still there's a little bit of a twist on that. The law of sines, the law of cosines. Oh, sorry. And one thing I forgot to mention the other day, I said I was going to give you the shortcut. If you don't know this, y equals 1/2 AB sine C. This is kind of fun. Let me show you this. If you had a triangle where this was 8 and this was 10, and this was 80 degrees, or you had a triangle where this was 8 and this was 10, and that was 110 degrees, which has a bigger area? Well, the short answer is they have the exact same area. Now, if you have a calculator, do this on your calculator now and you can double check for yourselves. So you could write 1/2 8 times 10 times the sine of 110 degrees. The idea with this is that C is the angle in between, not that corresponds with the non-A side, the non-B side. So if this is side C, then this is angle C, and this is actually important for the law of sines and the law of cosines. So I could say 1/2 10 times 8 times 10 times whatever sine of 110 is. Somebody already knows the answer. I don't know, but I could find out. Also 1/2 sine of 80 times 1/2 of 80 times the sine of 80 degrees. You get the same darn thing. You might ask, how can that, why is that? Here's the deal. The sine of this, if that's 10 and that's 8, and I wanted to find the height, because we know 1/2 base times height, right? 1/2 10 times the height. If I wanted to find that height using trigonometry, I would say that the sine of 80 degrees is the opposite the height over 8, and I'd put that on my calculator. Over here, same darn thing, that's the height, or that's the height. Why are these the same thing? Well, if you go back to the unit circle we talked about, oh, I'm a complete moron. Pardon me, that's supposed to be 100 degrees. Sorry, you guys are like, no one's put me in a QA and corrected me. Talking too fast. 100 degrees. And the reason for this, from the unit circle, if that's 90 degrees, and I have an angle of 80, it's 10 degrees off vertical. And 100 is 10 degrees off vertical. So the little tiny sliver away from straight up and down, away from straight up and down, will get the exact same heights. Okay? Last things. The law of sines is used for a non-right triangle. Let's say that's 50 degrees and that's 7 and this is 30, and I want to know what the heck x is. The law of sines simply says that there's a ratio of the sine of an angle to the side it goes with, my words, is in proportion to the sine of another angle on the side that it goes with, okay? So what angle goes with angle A? The side that's opposite it, just like with regular trig. If this is B, that's side B, and of course C and C. So if I wanted to find what x is, I could say that the sine of 30 degrees over x equals the sine of 50 degrees over 7. Put cross multiply, like I've talked about a bunch of times, sine of 30, 7 times sine of 30 equals x times sine of 50. I do it that way so I don't mistakenly do sine of 210 degrees, which would be a very, very different thing. I can put that on my calculator, and I know exactly what x equals, okay? The key with these things is what side goes with its own angle, goes with. It's kind of a silly way of thinking about it. Importantly, we would not do 30 degrees goes with x and 50 degrees goes with 7. It must be the sine of, okay? Last thing, and this is probably the most complicated thing to try to memorize, the law of cosines. It's basically a version of the Pythagorean theorem. That's where we started. I'm not going to show you the derivation of this. It's pretty cool, but it's a little complicated and you don't need it. And I don't want to blow anyone's brain up in the last 2 minutes, including mine. So basically, this is for non-right triangles as well. And it's a version of the Pythagorean theorem, c squared equals a squared plus b squared. And I did that on purpose to give myself a little space, minus 2ab cosine of c. Here's what matters. Whatever side I choose to put there must be the side that goes with, I mentioned that for the sines as well, goes with that angle. So let's quiz ourselves. Let's say that this is 30 degrees, this is 6 and 11, and that's x. How do I solve that? Well, it's really tempting to say x squared equals, because that's the thing you think you want to know. But we can't do that, because the angle, the side that goes with the angle is 6. So what we always want to do is say, what's my angle, what's my angle, what's my angle? Because with law of cosines, you're only going to be given one angle. 30 degrees is my angle. Ah, that's anchored me. What's the side that goes with it? 6. So I write 6 squared, and then everything else just falls in place. As long as I get that right, it's really hard to goof this up. Would then equal, let's think here, x squared plus 11 squared minus 2 times x times 11. I know it's a hideously messy looking formula. Cosine of, oh, I wrote that down wrong, cosine of 30 degrees. And after that, it's just algebra. So hopefully that was helpful. I did not get a worksheet of these things up for you guys yet. I will do that tomorrow. Thank you for joining me. Pretty much everything you ever need to know about trig. At least this frames for you what will be on the test, or what you could see on the test. Again, I'll put problems for you online tomorrow if you're interested in doing them, including the answers to those. Khan Academy, of course, has tons of stuff on there, and of course all the practice tests, including the ones that I put online last week. Next week, my favorite thing in the world to talk about, test anxiety, because kind of everybody has it. A little bit actually helps us. A lot is kind of a problem, and my interest is trying to have a conversation with you guys about how to be in the middle, in those sweet spots. So you have butterflies, you're a little excited, but you're not like about taking this test, because ultimately you're doing all this hard work to put things into your brain, and I don't want you to go to the test, and because you're too freaked out, kind of lose your mind, because then what's all this suffering been for? Thanks as ever for joining me. The recording will be up in a few days. We'll get some problems up for you in a few days, and I hope to see you guys all next week. Thanks for your hard work. Carry on.